Do the rest of you get those weird, short DIY/craft videos? Like the ones where somebody's trying to fix a gear by putting a bunch of bolts in it? Or where they're welding directly to bearings? Yeah, at this point I just keep watching them because I'm curious what they'll do next. But occasionally they give me good ideas. And this is one of those ideas. Well, not exactly this one. I stole this one from later on in the video, because the first one I made was a Christmas gift a couple years back. Well, what is it, you might ask? Mostly, it's a pretty cool lamp, but it's also an accurate map of the night sky, with about 1,000 stars. Now, ever since I made the first one, I've really wanted one for myself, but it took so much time to make that one. I mean, it spent hours getting all these lights in the right spot. And I haven't been motivated to make another one since then. Until today, when I decided I'm gonna automate it. Because why spend a couple hours making a lamp by hand when I could spend several weeks making a machine to do it for me? Or at least a machine that'll do most of it for me. But before we go on, I should get this back to the future, otherwise they're gonna know it's missing. Well, that's done. Now, how do I even go about making this machine? Well, first things first, I need to know what I want the machine to do. Now, I hear you asking, didn't you just decide you wanted the machine to make these lamps? And yes, I did. But how do I actually go about making one of these lamps? Well, there's 3 big steps. First, I need to take a blank half sphere, like this, and drill a hole for each star, and then affix an optical fiber into it. Then, once I've got it like this, I need to fill it with concrete and let it cure. Finally, the mold is removed, the fibers are connected to the LEDs, and it's put in a nice base. Now, actually automating the entire process would be quite hard. Thankfully, much of the work is in step 1, where I put the fibers in the holes and drill the holes, since there's a lot of fibers that need to be put in, which is both very precise and very repetitive work. Thankfully, this is exactly the sort of work that machines are great at. All I need to do now is figure out how to design it and what I need the machine to do. In engineering speak, we like to call this coming up with design requirements. Now, for something like this where I'm automating a manual process, I like to go through it slowly and take notes on what I'm doing at each step. The goal is to break down a complex process into several simpler processes. So, let's go through it together. First, I'll need to drill a hole in the mold. Oh, sounds simple, right? Well, watch closely as I do this, and see if you can list all the different things I'm doing. Did you catch all that? To drill the hole, I had to correctly position the mold, turn on the drill, push the drill into the mold without the mold moving, take the drill out of the mold, and then finally turn off the drill. Now, it may seem like I'm overcomplicating something simple here, but remember, any machine we build can only do exactly what we build it and tell it to do. So it doesn't hurt to be overly precise. Now that the hole is drilled, I need to put a fiber into it. Just like before, we need to break this down into simple steps. I had to pull the fiber off the spool, then I had to cut the fiber to length, and finally I had to position the mold and the fiber precisely enough to get the fiber through the hole. Now, if I don't want the fiber to fall out, I also need to glue it in place, but even that is more complicated than it looks. Of course, I need to correctly align everything, I need to dispense the glue, and finally, the glue needs to cure before I can let go of the fiber. And with that, we're done. 1 fiber. Just $999 to go. But that's why we're building a machine to do this. Now, if we take a look at all these requirements, you'll notice there's a bit of overlap. Most notably, at each step, I needed to position what I'm doing relative to the mold. Now, I could build a motion platform for each individual tool, but it's going to be easier to keep the tool stationary and just move the mold instead. And with these requirements in mind, I can now start designing the mechanisms I'll need to make this machine. I'll start with the motion platform we were just talking about. I could use a Cartesian frame where you have a separate motion for the X, Y, and Z axes, and it could reach the entire mold, but we need some other mechanism to keep the tools perpendicular to the surface of the mold. But you might have noticed the mold is half a sphere, which means this is a perfect case to use spherical coordinates. Instead of using X, Y, and Z to describe position, like we normally would, we can instead use 2 angles and the radius. Since the project is about stars, let's use the astronomy name for these angles. The zenith angle is the angle from the top of the sphere to our point, and the azimuth is the angle from north along the horizon. Now, to move the mold along these angles, we can just put a motor on each axis. By rotating both motors, I can access any point on the surface of the mold, and that takes care of the math behind the motion system. However, there is another concern. For the machine to work, the motion system must be precise enough to align the fiber with the hole, which would be no problem if the hole was big, but I need the holes to be about 1.5 millimeters in diameter, and the fiber diameter is only 3/4 of a millimeter. This leaves me only about 1/4 of a millimeter of space around the fiber, which isn't very much. Now, it's not quite that bad. As long as most of the fiber is lined up with the hole, it'll go through just fine. So, plus or minus maybe 1/2 millimeter, which corresponds to about 1/2 degree at the stepper motor. Now, if you saw my last video, you'll know that this is more than the 1.8 degrees the stepper motor is capable of. So I think I'll just use the gearbox I made in that video. With that done, I can move on to the drill. Thankfully, I can just buy a fairly cheap spindle motor, then I'll use a MOSFET, which is basically an electronic switch, to turn it on and off from the controller. Next, I'll put it on some linear bearings so it can slide in and out, and finally I'll add a servo with a rack and pinion gear to control the position. The base of the fiber tool is pretty similar to the drill, with the entire tool on a linear bearing and a servo to move it in and out. The hard part for this tool is dealing with the fiber. And the first thing I need to do is insert the fiber into the hole in the mold. Now, the motion platform for the mold will do most of the alignment work, but since this will be 3D printed, having a bit of adjustability in the design wouldn't hurt. And the tip also needs to be pretty thin, so it won't hit any of the previously placed fibers. And a small brass tube is exactly what I'm looking for. I can easily bend it for small adjustments, and it's almost as thin as the fiber itself. Now the problem becomes, how can I pull a thin plastic fiber off a spool and push it through a brass nozzle? Well, that sounds exactly like what a 3D printer does, so I think I can just use a 3D printer extruder right here. And then all I'll need is something to cut the fiber. To do that, I'll just attach a razor blade to a servo, just like one of those office paper cutters. And with that, the fiber tool is done. Now, all that's left to do is apply the glue. But first, I'd like to discuss the different types of glues I could use here. Now, you may have noticed earlier I was using superglue when I assembled one by hand. Now, superglue is great. Super, even. But for my application, it's quite possibly too sticky. It's so sticky that any device I can think of to dispense it has a very real possibility of gluing itself together. Which makes me wonder, do superglue factories ever get stuck? If any of you work in one, please let me know. Anyways, superglue is out. What are our other options? Here, I've got epoxy, hot glue, and some UV glue. You might be wondering, why this particular selection of glues? Well, they're all glues that won't cure in the machine, but can cure quickly outside of it. Now, epoxy seems like the obvious choice here. It has 2 parts, it won't start curing until they're mixed, it can cure pretty quickly, and even when it's not cured, it's sticky enough to hold the fibers in place. However, remember that mixing thing? Turns out that's a problem. Now there are mixing nozzles you can get, but since the glue mixes in the nozzle, it'll also cure in the nozzle if left alone, and it'll probably take a couple hours for the machine to run, which is more than enough time for the glue that's stuck in the nozzle to cure. Alternatively, I could build some mechanism to mix the glue once applied, but as I say, the best mechanism is no mechanism. So let's see if any of the other glues will work better. Next is hot glue. And this is what I used the first time when I made the entire thing by hand. It seems to have everything we're looking for. It's very easy for a machine to apply, and there's no risk of it clogging the machine. One problem though is it doesn't actually stick all that well to either the molds or the fibers. But what if we could use another type of hot glue? Well, it's not quite hot glue, but 3D printer filament is pretty similar, and I won't even need to design a new system to apply it. I can just use one of the existing hot ends I have lying around. Unfortunately, none of the filaments I had on hand were any better at sticking, and I tried a lot of them. PLA, PETG, nylon, and even PVA, and none of them worked. Now, is there a type of filament that would stick? Probably. I suspect the fibers and the mold are made of acrylic. And you can get this as a 3D printer filament, but it's pretty expensive, and it has quite unpleasant and even dangerous fumes, so I think I'm going to try a different solution. Finally, I have this UV activated glue. This glue is very similar to the resin used by SLA 3D printers, and all you need to do to cure it is to shine some light on it, which makes it almost perfect for me. All I need is a way to apply it. The simplest way I can think of is to just use a motor to move a syringe. I'll spin a screw with the motor and attach a nut to the syringe plunger, so spinning the screw will cause the plunger to move in and out. As long as the syringe holds enough glue for the entire mold, I can just fill it at the start of the process, and it should work. Then all I need to do is put a UV LED somewhere that can shine light on the glue after it's dispensed, and it should cure it. And I can't think of any reasons why this wouldn't work, so I guess I'll try it. Now I've got a good idea of how I'm going to make each part. The motion platform to move the mold, a drill to put holes in the mold, the inserter to put fibers in the mold, and the glue applicator to apply and cure the glue. Now all that's left to do is put this together in CAD and build it. Thankfully, since this is YouTube, I can just design via montage. It's much more efficient. Well, that's not quite what I designed. Alright, well, it looks like some improvements got made to the machine while I was taking it out of the computer. Let's take a look at them. I think the most visually obvious change is the motion platform right here. So you might be able to tell, I replaced the gearbox motors I made in the last video with these belt drives instead. Now, I know a lot of you mentioned that these will be better, and you were alright. Turns out, belt drives better in almost every way than the gearbox, just a little bit larger. Another benefit I didn't really think about is now the back of the mold is completely empty. So if I take the mold off here, you can see that I can stick my hand through here, which is important because when the machine puts the fibers in, they don't hit anything. Here is what the motion platform originally looked like. And you can see that there is this hub with the motor in the center, and the fibers would hit it. I did think that this would be a problem, which is why I designed the hub in this way with this cone-shaped thing. So the idea was the fibers would hit this and they'd be deflected into the gaps here. It turns out, though, that 1,000 fibers is a lot, and it would cause problems. Related to that, you might have noticed that now there's this brown thing inside the mold. See, once the fibers are all in, I need to bundle them for each LED. So each LED gets a bundle of a couple fibers. And ideally, I'd like the fiber position on the surface of the mold to correlate to which LED it gets assigned to. And doing this by hand was really hard. Turns out, I just make this insert, and now, if a fiber comes in, perpendicular to the mold, it goes inside, and it's deflected into the correct channel. So then I can just bundle these and put them with each LED. And this actually works really well. You might have also noticed that there isn't a syringe here anymore. And it turns out that putting a clear syringe filled with UV glue near the light doesn't work so well. Now, I did think of this, and so I covered the syringe with this black tape in the hopes that it would block the light. And it mostly worked, but over long enough times, enough light would get through that the glue would cure inside the syringe. Plus, filling it was always really messy, and over time the plunger would leak, so I decided to change to a pump. Specifically, I changed to a peristaltic pump. So as the motor here turns, you have these bearings around it, which squeeze a flexible rubber tube and trap a volume of fluid between the bearings. So as the motor rotates, the trapped bit of fluid gets pushed all the way around. And the nice thing about this is that the fluid is always in the tube, so there's no danger of it leaking anywhere, and I don't have to seal any 3D printed parts. However, the downside is the bearings are constantly coming into and out of contact with the tube, which means there's moments in time when there's no fluid flowing through the pump, and when there's a lot of fluid. So the fluid ends up coming out in a bit of a pulsating manner, which makes it hard to control the amount of fluid dispensed, especially if the desired amount is smaller than 1 pulse, which is why I had initially avoided it. But then I realized I could just make a pump with smaller bearings and a smaller gap between it so that the fluid volume was the exact size I needed it. And this whole system works so much better than the syringe ever did. And finally, I wanted to talk about the actual nozzle for the glue system right here. Now, initially, I had just rigidly mounted the glue nozzle right next to the fiber nozzle. However, over time, some glue would accumulate on the nozzle and it would end up curing, and this would cause a big glob of glue to build up on the end of the nozzle, which would cause problems. So now I have it on this track here, controlled by a servo. When it's time to dispense the glue, it rolls forward and can dispense the glue exactly where it's needed. Then when it's no longer needed, it rolls backwards. Now there's still some glue that leaks out of the nozzle, however any excess glue now just drips down the nozzle and falls someplace else. And with that, the entire machine's working now. I'll say this whole machine took way longer than it should have, but it's so cool to finally see it working. Now, all I need to do is actually make the lamps. But I think this video has gone on long enough. While you wait for that, here's some footage of the entire machine working. And if you like this sort of project and you'd like to see more, please consider subscribing. It really helps me. And thanks for watching.